Okay, what's up, folks? So, gonna continue on. In the last video, we did the decoder for the rectified flow backbone, which is using UNet with ResNet blocks because we're using Celeb A data. So we have a small data set, relatively speaking, and we want to get results quickly. So we're going to use a model with inductive bias, which is the translation equivariance of convolutional nets. And we're going to use the skip connections of UNet to get good velocities. And we pass in our time step embeddings, right? So you can see we have our encoder with our downsampling. We have our mid block, and then we have our decoder with our upsampling, and then our velocity head. I should rename this actually. Well, yeah, I'm gonna rename this to V out projection, because in the future we're gonna be loading models and we're gonna be adding text velocity as well. So I want to okay, make sure we're ready for that. So okay, and then we have our training loop, right? These nice tight loops. And then I coded this inference portion, which I'm going to uncomment now. And we're just going to do this sample batch pixels, right? So every so often, depending on this inference peak number, once this modulo resolves to 0, as we're training, we're going to actually generate some samples. To do that, just like in the notes, we have to solve this integral. And we use this left Riemann approximation, right? So we simply pass. So what we do is we sample in X1, we sample from a standard normal, and then we go from 1 to 0 by performing this integral. So we pass in we move along this trajectory and we pass in where we are in the trajectory, and we pass in the time, and then we get a velocity and we scale the velocity vector by the delta time step. So that's what we're going to do right now. And we're just going to iteratively do that until we have our image. That's the data. That's the optimal transport path. We're literally going to do the transport from, we're literally going to do the nonlinear transport from from noise to image, right? So, okay. So, sample batch pixels. So, what are we going to do? So, we're passing in the image shape here. We're passing in the model in the image shape, and we're going to just use these values. Okay. So, what do we need? Okay, we're doing this, so we need noise. All right, let's get noise. So X1. X1 is going to be torch.rand and BCHW is going to be batch size and then image shape. Okay. It's like, can I just call this method yeah, it's gonna be tough to test this out. Yeah, It's fine. I should be able to just code this up. Okay. So this is BCHW. Okay, this is our noisy image. And we need to transport this to X0. So we need time values, okay? Right? So we need to iterate. We need to make this into we need to actually solve this equation. So we need to iterate. So we have x1, and then we're gonna add the prediction from our network to a delta t. So we need our time steps. Okay, so this is going to be torch.linspace. This is a perfect use for linspace. We're going to go from 1 to 0. Steps equals num steps. Device equals device. Okay, so now this is a list, and then we can say for t-val in t-vals, we can say xt, right? So we can say x is going to be equal to model times delta t. So x plus equals x, x equals x plus model times dt, where dt is going to be equal to 1 divided by num steps. Right? T-val, this is T-val. And we'll say this is X. Okay? Just to make it obvious, how about we just name this XT? So XT starts as a sample. Well, technically it's not, well, yeah, I mean, let's just call it X. X starts as a sample from a standard normal, and then we integrate, we perform this approximation, and we get our image. So, but wait, T is just a value, right? But we can see our model UNet pixel space. Actually, T is of shape B, right? T is of shape B. So we need to make sure that T is, actually, is T a tensor? Let's see. Well, let's do this. Let's put the debugger here and see what we get when we make a linspace. If it's a tensor, then I can just, use the notation I've used before to broadcast. What's happening? Okay. Linspace 1, 0, 16 steps. It's a tensor. So, but I don't know if I can, for I in t-vals, I don't know if I can just, oh, okay, yeah, it gives me a little tensor. Nice. Okay, cool. Well, so then I can just say, so this is going to be, right, so So if it's a scalar, it's just a single, it's a scalar, it's a tensor representing a scalar, then I can say boom, and then 1. Wait, no, I need to broadcast it. I need to use expand. I need to say expand B, and that will make it of shape B. It's different than I was doing above, right? So T val dot expand B. Yeah, that's going to give us what we want. That's going to give us what we want. So nice. Okay, so let's run our code. So inference peak number, let's make sure. So yeah, so every epoch, we're going to perform inference to see what things look like. So and then log dict. I need to make sure that I'm adding so we're going to have train loss, we're going to have val loss. We need to add train loss, val loss, and then log samples to grid, and then, okay, yeah, it's going to log commit is true. I think I usually have the epic. What's going on? What's going on? I don't think I really need that though, to be honest. It doesn't really bias anything. All right, let's run this. Let's see what happens. Oh, 34 minutes already. Wait, no. That was the last timer. I forgot to set the timer again. All right. Oh, I should have reduced the number of samples. Let's just reduce it. So we have number of sample size, say it's 8, batch size 1. Well, say batch size 8, sample size 8. Oh, well, then validation isn't going to have any. How about this? Sample size 8, batch size 4, and then how about I do P train length is going to be let's move that to here. Let's move that from the base to here so I can switch up time dim. So on the server, it'll be 0.9, but here it'll be 0.5, so that when I do a small sample, the validation step will still have, so it'll still have data in it. So batch size should be 4. Validation set and training data should both be size 4. So it should be one iteration. Yeah. And then we'll see how the sampling looks. Should be noisy, but at least should run. Received an invalid combination of arguments. Oh, this should be, yeah, rand. Okay. Torch.rand n 4222. Yeah, okay. That's fine. So if I say B, if I say B, C, H, W equals temp 2 and then temp, yeah, B, W. Huh. Doesn't like that? Why doesn't it like this? So if I say torch.rand n, I'm confused. You got me there. You got me there, buddy. You got me there, buddy. Image shape. Batch size should be 4. Image shape 3, 128, 128. But it should be, I should be defining image shape up here. I am not defining image shape up here, but yes, I am. Okay, well, let's run this. See what we get. Okay. Received an invalid combination. Oh. Ah, I see. I see. I see. Model. Image shape. So it's it thinks batch size. It's looking for batch size. Okay. Model, image shape. Okay. All right. So one thing I might have to do for DT, I shouldn't. The DT should be correct, but it should be correct. Even if it's not fully correct, it'd only be off by a few tiny decimal places. It's correct though. I probably should have set the num steps to be locally. We'll make num steps. Oh, well, it's not going to log it to weights and biases anyways. Okay. Num steps 100. Num steps 300. Yeah, my CPU is working pretty hard right now. CPU is working pretty hard right now. Maybe I should do batch size, it's just 1. It's taking a while. Let's do number of steps. So batch size is 1, num steps is going to be 100. Well, we can't visualize it yet. I'll visualize it. Let's do show samples. If config dot visualize local visualization is true. We'll do show samples. Okay. All right. Hopefully it'll spit something out. Because this looks right. Making a lens space from 1 to 0. From T vals. Yeah, multiplied by DT. Num steps. No. I mean. Forming inference. Oh. Yeah, this takes quite a bit of time. Why is it taking? Hmm. Hmm. Taking quite a bit of time. I thought it would go faster, honestly. I wonder if it's because this isn't a tensor. Does that matter though? I'm gonna try this. T-vals. Let's do this. Let's do this. Let's put a debugger there. Just to make sure all is well. This will give us our DTs as well. I'm just making a list where I'm actually doing the, because I know this will give us a tensor. I don't know. I just feel like it should be okay multiplying a literal by a tensor, but there's no reason for this to be taken for it to be taken as long as it was. I mean, I can hit continue and that should finish up pretty soon. Yeah, it's done now. Maybe that was the issue. It wasn't a tensor and it didn't like that. But it also, I return X is visualize, local visualization is true. If local visualization is true, it's returning X. We log the samples. Performing inference. Should be finished pretty quickly. Okay, boom. We're getting ready to start to see a face in there a little bit. So, yeah, we know it's working. This is good. I like this. I'm okay with this. I think we're right on track. Cool. So next video, we're going to load it into RunPod and actually get a full training iteration so you can see some faces being generated, and then we'll start to move on to cooler stuff. So yeah, thanks for watching.